This is Jack Jackson. Today we're going to be talking some more about finding antiderivatives or integrating. In this we're going to talk about the technique of integration by substitution. So remember, we've already looked at some basic integration rules or antiderivative rules in the last couple of videos, and really we've only learned how to find antiderivatives of really very few kinds of functions, really just three: constant functions, power functions, and exponential functions. Now the sum and the constant multiple rule allows us to expand that a little bit by things that are built up out of adding those things together and maybe multiplying by constant, so that would be things such as polynomial functions, for example. So we can find antiderivatives of those kinds of things, but really that's it so far. So what we want to do is open that up a little bit and see if we can find antiderivatives of some more interesting functions. Well, if we think back, when we looked at our derivative rules, the thing that really opened that up for us and allowed us to find more derivatives was the chain rule, also known as the substitution rule. Okay? And so the inverse of that is the integration by substitution. So integration by substitution reverses the chain rule. So the basic idea of substitution is to introduce a new variable, which is traditionally the letter u, and then we compute the derivative of u, du over dx, and substitute to change the variable from the original variable, say maybe it was x to begin with, and now we turn it all into u's. We also have to be sure that we substitute to get rid of the dx in the original problem and put it in terms of du. Now we're going to use the symbol du to mean du equals du over dx, the derivative of u with respect to x, times the symbol, differential symbol dx. And so the hope is that this new integral of a function u is something we can integrate or anti-differentiate using the basic rules. So we're going to look at a few examples here. Okay? So I'm going to start with a couple easier examples, and then we'll get to a few a little bit more interesting ones. So we want to find the following family of antiderivatives. The antiderivative of x to the fourth, x plus 4 to the 7th. So when we look at a function like this, we see it doesn't automatically fit one of our just basic rules, but we can make a substitution to make it fit. So when you see this, you want to try to decide, well, what do I let u be? Okay, and sometimes it's a little bit of a trial and error thing, but mostly there are certain clues. So when you have a variable base and a constant exponent, a thing to try is to let u be that variable base, and that's what we're going to do here. So the first thing you do is try to figure out what u is, and you're going to make that determination. You're going to write that down. So you're going to write down u equals x plus 4 right here. Then the next thing is to find du. So the du is the derivative of the u with respect to x times dx. So the derivative of x plus 4 is just 1, so du is just 1 times dx, or just dx. Now, if we look, we can make an easy substitution here. X plus 4 becomes u, and dx becomes du. And with that substitution, now we have an integral, and our antiderivative, and it has no x's in it. It's all u's. Well, this is a function that does fit one of our basic rules, and it's a power rule, and so it's pretty easy to do. We just add 1 to the power, so 7 becomes 8. We multiply by the reciprocal of the new power, so we multiply by 1/8 in the front. Of course, when that last integral sign disappears, we always put plus c because we're looking for the entire family of antiderivatives. Now, we introduced u, so we need to go back in terms of x. Well, u is x plus 4, so everywhere there is a u, we put a parentheses with x plus 4 in it, and we have our final answer. Now, anytime you do integration by substitution, and you check it by doing a derivative, you're going to be using the chain rule, i.e. the substitution rule for derivatives, and you're going to be using exactly the same substitution. In this case, u equals x plus 4. So check it out here. We take the derivative of our answer. We're taking the derivative of 1/8 x plus 4 to the 8th plus c is the derivative of 1/8 u to the 8th plus c with that same substitution, u equals x plus 4. Now, of course, as always, we do the derivative of the sum. It's the sum of the derivatives, and the derivative of constant is 0. So that c just disappears. And now we take the derivative of this part right here in the front, which is a power function with the coefficient here. So we take the old power 8 times the old coefficient. 8 times 1/8, that cancels to leave 1 for the coefficient. The power 8 goes down to power 7. And then you have to use the chain rule. It says you have to take the derivative of the u. Well, the derivative of x plus 4 is just 1, so we get u to the 7th is x plus 4 to the 7th power. Of course, as always, we can always check any derivative problem using a TI-84 level calculator here. We let y1 be our, we check a derivative or an antiderivative problem. We want to take the thing that we want to find the derivative of is y1, and the derivative of it is y3, and let y2 be the numerical derivative. Check that y2 and y3 are the same. So as far as an antiderivative problem, checking this, our answer is what we want to take the derivative of. So our answer goes in as y1, in other words, an antiderivative. I left off the plus c, but you should be able to put in plus any number you want there, and this should still work. So we take that and put it in y1. y2 is always this way, the derivative of y1 with respect to x. That might be on your calculator if you have an older one as nderiv of y1 comma x comma x. Okay, you can see that in a previous video, more detail about that. But either way, it's math 8 on the TI-84 or 83 or even TI-82 calculator to work. And the y3 then is the original integrand right there, the x plus 4 to the 7th. We check to see the tables for y2 and y3 match, and of course they do. If we want to, suppose we have, we're given that the derivative of a function is this x plus 4 to the 7th, and we want to find a specific antiderivative. From what we've done above, we know the family of antiderivatives is 1/8 x plus 4 to the 8th plus c, so f of x is that for some specific value c. How do we find the specific value c? We plug in the point that we know. In this case, x is 1, y is 4. So we put a 1 where the x is, the f, where the f of x or f or y is, we put 4. And we just work this out. 1 plus 4 is 5. 5 to the 8th is 390,625 times 1/8 is 390,625 over 8. That's plus c equals 4. Subtract that fraction from both sides, get a common denominator. 4 is 32/8. And when we do that subtraction, we get negative 390,593 over 8. For c, take that value, plug it in for c in the original, and now we have our function we're looking for. If we took the derivative of this, we would get x plus 4 to the 7th, and if we try to plug in 1 for x, we will get 4 out for y, and it meets the conditions that we were after. Okay, well, what does this have to do with integration? Well, we can use the fundamental theorem of calculus to find a definite integral here. So if we're going to integrate from -2 to 1, we can do this problem. Now, one thing that is important here is that we have to note, okay, what happened there? Let's try that again. We need to note that the function is continuous on this interval in order to apply the fundamental theorem. Okay, so what does this tell us? It tells us that we can find this antiderivative and then just simply evaluate at both endpoints, and we can then subtract those two things, and we have the value of the definite integral. That's what the fundamental theorem tells us. So let's do that. Alright, so we've already seen that an antiderivative is 1/8 x plus 4 to the 8th power. We don't have to worry about the plus c when we do a definite integral, so we just evaluate that from -2 to -1. What that means is you take that formula of the antiderivative, any antiderivative, plug in the top number for x, then subtract, put in the bottom number for x, and just work this out. So -1 plus 4 is 3, so we have 3 to the 8th here. And -2 plus 4 is 2, so we have 2 to the 8th there, and they both had the 1/8, so we factored that out. 3 to the 8th is 6,561. We could certainly work that out by hand, or we could use a calculator for it. 2 to the 8th is 256. Subtract, and we get 6,305, and then times the 1/8 is 6,305 over 8. That's an exact value. We could do division. We could do long division by hand and do this, or with the calculator, and we see that that's exactly 788.125. Typically speaking, when we want an exact answer, we'll usually prefer fractions, because fractions will give us exact answers, whereas decimals sometimes will be rounded off. Okay. However, if it terminates, of course, then that's also an exact answer as well. So both of these versions are actually exact answers. And of course, if you do this on the calculator, do the numerical integration on the calculator, this is math 9 on a TI-84, or 82, or 83, and we put this in. If it's a newer TI-84, it looks like this. If it's a TI-83 or an older 84, it would look like FNINT of, put in the formula x plus 4 to the 7th power, comma x, which is the dx here, comma, the lower limit, -2, comma, the upper limit, 1, -1, and then close that out and enter. Alright, let's try another example. Now this one looks like it's a lot more complicated, but integrals are sometimes deceiving. Trying to find antiderivatives is a bit deceiving, because sometimes you can see a function that looks very simple and it's actually very difficult or even impossible to find a substitution that's going to give you a nice antiderivative built up out of elementary functions. On the other hand, sometimes you get something that looks kind of nasty, but with the right substitution it becomes a very simple integral to do, and this is the last case. So obviously this doesn't fit one of our basic patterns just like as it is. It has to be manipulated a little bit. We're going to do that with substitution, and again we have basically a variable base and a constant power. Remember that a radical is just a fraction power, a constant fraction power, 1/2 in this case. So we're going to let u be that variable base, 1 minus 3x squared, and we're just going to see if it works out. So a little bit of this is guess and check. So we're going to let u be the 1 minus 3x squared, do the derivative of the u to find du. Well, derivative of 1 is 0, the derivative of -3x squared is -6x, and then of course we always have our dx. So du is -6x dx. Okay, wait a minute, this is going to work out just nicely, because if I rewrite this square root as 1 minus 3x squared to the power 1/2, and then I group what's left, the -6x and the dx all together, then this part that's grouped becomes du. And this other part that's grouped here becomes u. Oh, that's nice. That works out just perfectly for us. Okay? And so in fact this 6x in the beginning, -6x, didn't make it more complicated. It actually made it easier, because it made the substitution work out just right. So now we have the antiderivative of u to the 1/2 du. Okay, that's not hard. We add 1 to the power. 1 plus 1/2 is 3/2. Multiply by the reciprocal of the new power, that's 2/3 out front. Our integral sign disappears, so we put plus c to get our entire family of antiderivatives. Now I'm going to simplify this, or rewrite it, not necessarily simpler, but just a different way, more consistent with what we started with. U to the 3/2 power is u to the 1 1/2 power, so the 1 power is u to the first, the 1/2 power is the square root of u, and so we got that in a reduced radical form. Now I'm going to substitute back in. U is 1 minus 3x squared, so that substitutes in both places for u here, and now we have our final answer. Let's check that one. Okay. Well, we check it by doing a derivative, and guess what we're going to do? We're going to do exactly that same substitution. U equals 1 minus 3x squared. And so when we do that, this becomes the derivative of 2/3 u, square root of u, plus c. I'm going to write u to the square root as u to the 1/2, then u to the first times u to the 1/2 is u to the 3/2, and so it boils down to this here. Take the derivative there. Of course, the derivative of c is 0, as always. Then we take the old power, subtract 1, becomes the 1/2 power, and then we, before we do that, I'm sorry, we take the old power times the coefficient. So 3/2 times 2/3 is 1. Then we subtract 1 from the power and get 1/2. And then you have to take the derivative of the u. Well, the derivative of the 1 minus 3x squared is negative 6x. Notice we used the chain rule there. We did a substitution. When we do the chain rule, we're taking the derivative with respect to x. This variable is u. Got to remember to multiply by du over dx. Okay, and of course the derivative there is negative 6x. Substitute back. I wrote that in the front. I wrote the square root of u back in terms of x there, and that is exactly back to the integrand that we started with, and so it checks. We can also, of course, check it with our calculator by putting our answer, this 2/3 1 minus 3x squared times the square root of 1 minus 3x squared. You can put plus a constant if you want, or just leave the constant 0. Put that in as y1. y2 is the derivative of y1 numerically, and y3 is the original integrand, and check to see that tables for y2 and y3 match, which they do. If we want to use this technique to compute a definite integral, say from 0 to 1/2. Now, notice that we do have to check that this function is continuous over this interval, and from 0 to 1/2 it is. In this particular case, we might actually, let me do a little bit extra work here and show you something. We might actually look at the domain of this. So the part that's underneath the radical is 1 minus 3x squared. Well, that part has to be greater than or equal to 0 for this to work out. So that says 1 is greater than or equal to 3x squared. Okay, which, let me rewrite it this way. That's another way to say that is x squared is less than or equal to 1/3. So if x squared is less than 1/3, then take the square root of both sides. Okay. Now, when I square root both sides, when I square root x squared, I actually get the absolute value of x. And on the right side, another way to write this would be 1 over square root of 3, or I could actually even write it as square root of 3 over 3 by multiplying both sides, top and bottom, by square root of 3. So this says that x is between the negative or opposite of that square root, and that is less than, that square root is less than or equal to x, which is in turn less than or equal to that positive square root of 3. Now, square root of 3 is a little bit bigger than 1, right? Somewhere between 1 and 2. So when you do divide by 3, well, let's see, I guess the real question is about where is the square root of 3. Maybe we should get a decimal approximation for that. Okay, and so the square root of 3 and then divide by 3, that's approximately 0.5 here. Square root 3 and then divide by 3. There we go. So that's about 0.57735022692 as far as my calculator go, and the opposite of that okay, so that's the domain here of this function. Okay, now, so the question then becomes, is this function continuous on that interval? That's important because you can't use the fundamental theorem without that. But we noticed that our interval is from 0 to 1/2. Well, 1/2, this 0.577 is, or square root of 3 over 3, that's a little bit bigger than 1/2. And of course 0 is definitely in the middle of this interval. So this stuff between 0 and 1/2, the function is defined there. The negative 6x part's always defined. The multiplication is defined. It's a matter of the square root being defined. And this function is continuous where it's defined. So in fact this is going to work. Now when we do a check with the calculator, we're going to have to make sure our x's are in between these values, or we're just going to get error messages. Okay, so we can use the fundamental theorem. That's important. So now we can do that. We find an antiderivative, and there it is, and we just evaluate from 0 to 1. Same antiderivative we just worked out a minute or two ago. So we take this function, plug in 1/2, same function, plug in 0. Let's see what we get here. 1/2 squared is 1/4, times 3 is 3/4. So we got 1 minus 3/4 is 1/4. That's here, and then that's the square root of that 1/4 here. When we plug in 0, 0 squared is 0, times negative 3 is 0, plus 1 is 1, and so we get a 1 here and a 1 under the square root. Of course, square root of 1 is 1, times 1 is 1, times 2/3 is 2/3, and that negative makes it minus 2/3 there. Square root of 1/4 is 1/2. The half cancels the 2, and so we end up with 1/3 times 1/4 is 1/12. Get a common denominator of 12, multiply top and bottom of this fraction by 4, and we get 8/12 is the same as 2/3. 1/12 minus 8/12 is negative 7/12, which exactly in decimal form is negative 0.583 with the 3 repeating. Negative 0.583333333, for example, forever. Okay, now let's check it. Let's say if we just check this using our calculator, we can just integrate that function, and I already had the thing in as y3, so I saved myself a little typing by just typing it once. I could, of course, type the formula of the original integrand right there instead, and that turns out to be, well, that, and in this case it changed it to a fraction, and it came out correctly, exactly as a fraction. So in this case, the calculator told us an exact answer. Alright, so now I have a few problems that I'd like you to work. Okay? So what I'd really like you to do is to write down these problems. I've got about 6 antiderivatives here, or families of antiderivatives to find, and 3 definite integrals, and all of these involve substitution of some kind. So I'd like you to write these down, press pause and write these down, go work them, and then come back and check your answers with the rest of the video. So go ahead and press pause now. Okay, well, let's continue on and look at some of these exercises. Actually, you know what? Let's come back in the next video and check these exercises. So check your answers with the solutions in the following video.